I'll see how far I can go to compress the whole thing. So I don't know if you can see my screen. You can see my screen, right?
Yes, we can see it.
Oh, great.
Yeah, we can see.
So it's still okay, great. So it's still in addition to the model interpretability we talk about. I remember we are still in this part of the machine learning pipeline. So by the time we finish, the next pipeline we'll be talking about is model deployment and how to build web application. So like I told you guys from the onset, the aim of this class is to make you to have this data product at the end of every project or data-driven project you do. Now, when we talk about data products can be in form of a web application or a mobile application. It can also be in form of a manuscript or a written report. So most of the time, it's if you are doing for organizations, some of them may request for an app that or what we call a visualization dashboard. So that's where you see some people create these visuals for them, interactive visuals with things like Tableau and the rest. In as much as those Tableau are very good, but one of the issues I think it's that sometimes if you are not there, another person cannot come and recycle it. So that's one of the area why Python is quite useful, because when you build these things and you put the script, any other engineer can come and study what you have done and will see how to improve upon it. So one of the issues we are having when you're using those static kind of softwares is the fact that it's kind of operating in sort of like a silos. So you need to really do a lot of upgrading. You need to also get the APIs by purchasing the keys and all that. So it's kind of the open source is much better. So things like R, Python are very useful because they are open source and the community of people working on those things are very large. So the Python, for example, is almost like the English language. You will see a lot of people from all over the world. So it's very hard that you will confront an issue that someone else have not encountered before now. So based on that note, like I said, we are still in this part of the machine, and especially peeping inside what is happening in the model is quite a big problem because we said it's a black box. So, and if you understand the black box, we don't really know what and how the machine is arriving in making their decision. So, in order for us to further dissect the outputs of the machine learning models, we try to build sort of surrogates, or we try to build sort of interpretable models that would unveil or unpackage what has been packaged to us in a black box. So that's why we talk about all this stuff about interpretability. Now, today, if you notice also, in the previous classes, I make emphasis on different types of interpretability approaches. And we also talk about the global explanation, and we did talk about the local explanation. Now, when we talk about the local explanation, basically it's more like we are zooming into the samples. We are going back into each sample to unravel it to say, okay, what are the contribution of, let's say, each feature and also each sample. So it's like when someone talk about something being at a local level, it means that you are leaving all the whole universal space and zooming into a particular area of concern, and then you build explanation. Because these black box are, imagine if you are using something like deep neural networks that has millions or even billions of neurons. By the time you look at these networks, it's very hard for you to explain everything that is happening. So what you normally do is to zoom into a particular network or layer of that particular convolutional neural network, and then you begin to try to understand what is happening. Then so in order for you to understand it, of course, you will have to build models around it or surrogate models around it. So that area you zoomed into is a local space. So just like looking at the Earth from outside the space or a telescope, you see that we are in the solar system. Then when you zoom into a particular planet, you said, okay, that's a globe. And then inside that planet, you decide to say you want to zoom further into a country. And then inside a country, you can say, I want to zoom up further into province or state or even councils. So the same way, you know, when we talk about this explanation, you continue to zoom into them, so you could be able to understand what is happening at that local level. So we did look at SHAP last week, where we said SHAP it's also can also serve as a tool for local explanation. We could also use for global explanation. Then we also briefly talk about line, but I didn't show you guys how line works. So today we're going to zoom into the line approach. So the line approach is a local model agnostic method. So again, when we talk about it, we are trying to understand everything at a local level. So that's why we say it's a local model agnostic approach. Now, when we say line, it's not the line that you know, but it's an acronym for the local interpretable machine learning explanation. Now, the line first spring up in 2016 in a particular conference paper called Why Should I Trust You? Or something, I think, if I'm not mistaken. So but I'll try to get the citation, of course, for you guys to, if you want to read more about the approach on how the line starts. So in similar vein like the SHAP, but in the case of the line, you're not looking at the game's theory, like we said, from SHAP, but instead we zoom into the contribution of the futures, and then we begin to try to understand how faithful these futures were in explaining the predictions for us. So in this case, the fidelity of the model is very, very important to us. So we had several components, and I wouldn't want to bother you guys with the mathematical part, but if you are interested in the mathematical part, of course we could go into it and see how we could be able to express the equation, and we look at each component that is inside the explanation. So like I said, let me not bother you guys with that, but just know that at the end of the day, we are looking at how faithful these futures are, in explaining these predictions that we have. Having said that, um, today we are going to, of course, start with the hand-on section on these areas. So remember to always install the packages that we are going to be using. So if you don't have these packages, always install it. Remember, if you don't have the package, of course, you will run into errors. So always try to have the package. And if you recap from the previous class, like I said, that SHAP is based on game theory, where each of the individual features have to work together in order for them to contribute or make a contribution towards arriving or pushing that prediction forward. Then we said the advantage of the SHAP is that it provides us with consistent and additive future attributions. It offers a comprehensive global understanding of the model. And we said one of the common use or cases or models that we apply SHAP a lot is the random forest and also the gradient boosting and neural networks as well. We apply them, but basically they do very well when we have a tabular data set. But sometimes when we begin to have image or text data, you will begin to see we can begin to consider other explanation approach. And I pray to have time so we could look at how we could apply them in other cases, because it's not always that data set will be looking friendly. Sometimes you have to scrape the data. Sometimes you have to work with images. So in those kind of situation, you have to change the approach that you use. It could be SHAP, for example, trying to zoom into those resilient features that it identified from, let's say, an X-ray image. So, but in this case, those things changes. The explanation changes when we're dealing with a different kind of data set. Now, we said the SHAP stands for local interpretable model agnostic explanation. And then we said the line approximates the behavior of the machine learning model around a single instance by training a simpler interpretable models like linear regression, decision tree, or rule-based methods. Now, like I said, we zoom into a particular part of that model prediction that we have. So by the time we looked at it, we can be able to try to now say if this part of the model is behaving like this, there is tendency that the other parts of the model is going to behave that way. And this have a statistical backup. You know, if you know statistics very well, you will understand if you do a sampling theory, you would see where we prove that the sample mean is equal to the population mean. I think that's like one of the first lemma or theorem or so that you come across in sampling technique. So what am I trying to say? The behavior and the reason they come to arrive at that is because of the behavior of the sample, of the sample when it's being taken from the population. The sample is likely going to have the same behavior with the population, although one of the setback of the sampling mean that, like we always used to say, it's the fact that it's not sensitive to outliers. So because of this lack of sensitivity to outliers, it will always average across the samples. And when it does that, you could have some issues because there are some samples that may be behaving in some sort of erratic manner. And that's where we now begin to talk about some other descriptive statistics like the median, the mode, and so on and so forth. But today it's not what I really want to emphasize on. I just want you to know that what it does is it focuses on a particular part of the model, and then it tries to build a simpler model around it to approximate it. And sorry, I don't have visuals to show you these descriptions because of the time we take to prepare these materials, but if I happen to lay my hand on one, I could show you how it behaves. Now, the perturbation base, so what it does is that it perturbs that particular input data to observe if there will be changes in the prediction, and then it fits the local surrogate model. So when we talk about this perturbation, now when we say we perturb something, is that you see a situation where you try to tweak that particular instance to see if that how faithful is that particular input in making that prediction. So you try to like uh, build some sort of a noise around it, do some sort of twerking and play around with it to see does this really change, because the robustness of the input feature matters a lot. There are some features that if you remove them from the prediction drops terribly. And there are some of the features when you remove them, you still see the prediction does very well. And then there are the combination of some features or inputs that can give you very high accuracy in some cases. So all this approach, what the line does is kind of perturb this input to see how it does when it fits in a simpler model. So let's say you train an XGBoost model, and the XGBoost model identify, let's say, 10 features that are contributing to the accuracy of the model, or for example. Now, what the line is going to do is now going to play around with these 10 features that the XGBoost have identified as the most relevant features by now perturbing them as the input for the surrogate model that is going to build. Remember, the output is coming from a complex model already. So that it will take that output of that complex model and fit it into a more explainable, interpretable model like linear regression, for example, or decision tree or rule-based other algorithms. So by so doing, it could now be able to tell us the behavior of those features in that particular space. So the advantage of the line is that it's faster and also simple to implement. It works well when you want to explain a specific prediction rather than the entire model. So, like I said, it's a local explanation. So it means you are focusing on a particular part of the model. So the common use cases is explaining prediction for text classification, image classification, and also tabular data models. So like I told you, there are different kinds of data sets, and AI works with all of them. So if you have text data, AI will still work with it. If you have, in fact, even if you have satellite image data set, AI still works with it. Depending on what you have, your model could still fit into it. However, as beautiful as the LIME approach looks like or sounds like, it also have limitations. Some of the limitations of this approach is instability. So the line can produce different explanation for slightly different runs or perturbation of the input data. This is because it relies on randomly generating perturbation to create a surrogate model. So that's one of the problems, because this model, when you want to, like I emphasized earlier, you perturb something by, so you randomly altered it. Sometimes you can even generate or create some noise around that to see how faithful that input will be. So because of some of this, this has to rely on this randomization approach. So because of that, you cannot really pin it on one stance. I don't know if you have used ChatGPT. Of course, you must have, because it's the popular thing in these days. You will see that you don't really get the ChatGPT give you the same output that it gives you from, even when you put that same input into it. Each time you give it, it rephrase it. You give it kind of rephrase it. So that's what we mean by saying with, it's perturbed so such that you cannot, specifically have this output coming out the same all of the time. So each time you do it, it generates and all that. So locality. The line is designed to explain prediction locally for a single instance. It does not provide a global understanding of the model or how features interact across the entire data set. So these are one of the things you need to know about it, because one of the things is that these features, or one of the criticism of these approaches is these features cannot work in isolation. You cannot tell us that they are not interacting with each other. So why do you want us to trust it? You're always telling us, for example, this, the line want us to believe, that it is always this one man or one man show, like we see currently in the Nigerian political space, where APC wants to bully everybody and be the one party system, you know. So the life cannot be one man's show. We have to all work together in order for us to build a better society. So that neglect that comes from the the fact that SHAP focus on one particular part, like one particular instance at a time, is wrong. For example, Nigeria has 36 states, but you see a lot of focus being given to Lagos and Abuja. Nobody cares to talk about other states like Yobe, like Katsina, like Sokoto, Zamfara and all that. But these places are going on flames. There are lots of activities of bandits and killings going on in these areas, but they were not talking about it because that's not where the money or the administration interest is. So stuff like that. So, but you see that when you want to develop, when you are talking of Nigeria as a whole, you have to carry all the pieces together in your hands for you to say you're building a nation. So that neglect that we are having for these interactions, it's one of the limitations that we have in the issues of SHAP. And the fact that, of course, it doesn't look at the global explanation. For example, you can't just look at only Abuja and Lagos and conclude that Nigeria is doing well. Even in the Abuja and even in the Lagos, by the time you zoom into some slum areas, you will not see the presence of government. So when people talk about Lagos and the rest, they could only then they focus on the tush areas like Lekki, VI, and Banana Island, and so on and so forth, or Abuja, and they talk of Gwarimpa and all that. They ignore the fact that there are other slums around these places that do not have the presence of a pipe-borne water, electricity, or even good roads. So stuff like that. So the fact that it neglects that global view of the entire model is the limitation that we have with the SHAP approach. Now, another limitation is dependency on perturbation. The line has to depend on that randomization that you have to do each time. You have to generate these artificial things that are not really part of it, to see if this. Remember, the whole thing is surrounding fidelity and faithfulness of that particular future or input to the model prediction. So the fact that we have to each time rely on that perturbation to see how faithful that explanation is doesn't make sense. Sometimes, okay, not you won't say all the time, just some of the time. So poorly choosing perturbation may lead to inaccurate or misleading explanation. Now, one of the issues around this explainable AI stuff is the fact that we don't have this one acceptable way of doing these things. So, and I think it's even a general issue around data science that the way I could approach something is different from how another person could approach it. So we don't really have this unified platform or consensus on certain issues. So someone can decide to say he wants to use SHAP, and so another person could say, no, I will want to use LIME or some other explainable AI technique approaches. So this whole thing that you have to rely on this perturbation, it's not really good at some point. Then remember, surrogate model, it's more like a simplification. When you talk about surrogate itself, it's like you're saying this thing has failed, so let's give it to this person. So it's like you are transferring the responsibility of the model explanation from the complex model to a more simpler model to do the job. So just like we see in Nigeria today, you see the president running away and delegating governors to take care of insecurity, while he said the security of any country issues stop at his desk. So here's the complexity there that's supposed to address the issue, but rather he wants to put it to a surrogate. So you see, APC never accepts failure. They tell you, you could see recently the JAM that was released. They came out and said the reason the student failed is because they have shut down the miracle centers and also by introducing the CBT stuff and all that. That's bullshit. You can't write an exam where your students, 70% or 80% of them are failing. That shows there is a problem with the system. and the people managing it. You should not be happy with failure. You should question it and see why it's happening rather than trying to justify it in praising your own backwardness. So the same thing, you have to understand what is happening in that complexity. Why do we have this? Okay, so simplification relying on this surrogate doesn't really explain the behavior of the model entirely. So another fact that the future dependency assumption, the line assumes that the futures are independent and then perturb the data, which might not hold true for the data set. Like we said, multicollinearity is a very strong issue because it carries lots of baggages in itself. So the fact that this explainable or interpretable framework, they do rely on the fact that these features are independent of each other, which is not true in some cases, is very, very important. So another very important thing I want to also talk about is interpretability versus fidelity trade-off. So the surrogate model used in line is interpretable but may have low fidelity to the original model, especially for highly nonlinear model. Remember what I said, you are transferring the responsibility from the complex model to the simpler model. However, there are other things I highlighted like high dimensionality data challenge, limited support for sequential and structured data, and so on and so forth. Having said all that, you know, no, like I always say, model is the simplification of reality. No model is perfect, So this whole thing, the aim is not for us to build this perfection, but to help us to understand this thing in a human-friendly way. So we will not settle down more on the criticism part of this limitation or of these approaches, but rather we would look at them, take note of them. So when we are writing our report or we are building systems, we will be able to emphasize so others can build on some of these limitations. Remember, the aim of knowledge is not just to identify these gaps and critique them, but rather for us to look at where others have built upon and then we build our own. Knowledge is a continuous spectrum. So wherever you find yourself on the ladder, you try to extend it forward for others to also build upon. So having said all that, we will continue today looking at the breast cancer classification problem from our last class. Now, like I said, I would have loved to look at so many areas in the course of this class, but my interests or domain expertise really or heavily relied in the area of health, biomedical informatics side. So that's why most of the time you see me, I bring in these examples because that's where I feel much more comfortable to explain these approaches to you in a way you could understand better. But feel free to transfer them to your areas of expertise. Whether you are in economic sector, you are in climate change, you are in agriculture, you are even in the computational side or industrial side,